Okay, perfect. All right. Hello, my name is Calvin, and Gary and I are going to talk about our experience on the Vellvm project for formalizing LLVM. Before we start, we'd like to acknowledge all of the collaborators, institutions, and grants which have made Vellvm possible. There's a lot of them. So this talk is going to be a bit of a whirlwind introduction to Vellvm, a formalization of the LLVM IR in the ROC proof assistant. For this talk, we'll give a brief overview of LLVM, its complexities, why it's worth formalizing, and we'll discuss the state of the Vellvm project and its overall structure a little bit. We're going to briefly talk about our experience on such a large formalization project in ROC, what's working well, some pain points we've encountered, and what we'd love to talk to some people about. And finally, Gary will conclude the talk by talking about some of our differential testing work. So LLVM is a common compilation framework. It's used by a variety of front ends in order to generate efficient native code. And at the heart of LLVM is the LLVM IR, which is an assembly-like language which can be used as a shared compilation target for many compilers. This intermediate language also enables shared optimization and analysis passes. So LLVM itself is a bit like a high-level assembly language. Translating C programs to LLVM IR is fairly straightforward, as these languages operate at a similar level of abstraction. LLVM is just a bit more verbose. It has more assembly-like instructions and more explicit branching. But notably, LLVM IR abstracts away many of the details that you would find in a typical assembly language, such as the usage of machine registers and calling conventions, sort of. So LLVM IR is actually quite a big language, which makes it difficult to understand. For instance, here's the table of contents for the informal language reference. It's kind of intimidating. And even though LLVM is a large language, a lot of the complexity arises from how small features interact with one another, especially when we consider optimizations. To demonstrate this, let's just zoom in on one little feature of LLVM called an ondef. Ondef values are used to represent indeterminate bit patterns that you get in situations like when a variable is uninitialized. Ondef is useful because it gives the compiler additional flexibility. We don't have to keep track of a specific arbitrary value for an uninitialized variable. Its value is allowed to fluctuate over time, which can enable optimizations and ease register pressure. This is a somewhat artificial example, but because x here is not given a specific value, the compiler can assume that it can take on whatever value is most convenient for it and leads to the best performance. In this case, the compiler might choose a value which avoids the expensive branch. Ondef values can interact with optimizations in complex ways, however. Sometimes they allow for more optimizations, as in the previous example, but ondef can also complicate certain kinds of p-pole optimizations. So for instance, we can't transform a multiplication by 2 into an addition if the value being multiplied is ondef. Multiplying an ondef value by 2 gives you a non-deterministic even number as a result, but adding a value to itself, adding an ondef value to itself yields a non-deterministic set of all possible numbers, because the ondef value can actually take on a different value at each usage. And so these results aren't equivalent, and these instructions therefore can't be used interchangeably. So some features of LLVM have complex interactions, particularly in the context of optimizations. It can be tricky to know what optimizations are valid with all of these subtleties, and this can lead to end-to-end miscompilations. Indeed, features like ondef are complex enough that many miscompilation bugs have popped up because of it. For instance, the Alive project has run into so many optimization failures due to ondef that they had to automatically filter some of them out. So let's talk about how we hope to wrangle LLVM. LLVM is an important language used by many compilers, but it's a complex language, and subtle interactions between features can lead to miscompilations. Building a formal specification of LLVM in ROC should help us understand all of these subtleties and provide us with a platform with which we can verify the correctness of various optimization passes. This is the goal of Vellvm. The structure of Vellvm is roughly as follows. We're going to take the informal specification of LLVM and convert it into a formal description of the language in ROC. Naturally, we have an abstract syntax tree for LLVM IR in ROC, and we will model control flow by denoting this abstract syntax tree into an interaction tree. Interaction trees are a kind of co-inductive free monad, and we use them to represent program traces. The co-inductive nature of I-trees allows us to represent possibly non-terminating programs. And using the free monadic structure of I-trees, we can divide the language into events, which can be handled modularly. In Vellvm, these events are things like the state of the local and global environments, memory, as well as exceptional conditions like undefined behavior, and so forth. In this particular diagram, different types of events are seen as different colors of boxes. And events in our semantics are initially abstract, and we consider every possible interpretation that an event may have, which leads to the branching structure that you see in the diagram. Events are given specific meaning through event handlers. Interpreting events removes them from the tree and gives us a specific structure for the event, which collapses the branching structure of the interaction tree. Here, the orange events have been interpreted, and afterwards we have a more refined understanding of the behavior because the handler told us what the orange events actually meant. So for instance, these events could be representing loads and stores from local variables. And in that case, before handling the local events, you would only know that some value was loaded from a variable x, for instance. But after handling the local events, you would know the specific value x had at that point in the execution. And the value will no longer be abstract. Notably, some of our events, like memory allocations and also the handling of undef values, are non-deterministic. When handling non-deterministic events, instead of refining our interaction tree, we get a set of possible interaction trees for each possible non-deterministic choice. In Rock, we use prop to represent these sets. And using this, we can capture every possible execution that an LLVM IR program can have. So for instance, we collect executions for every possible way that allocations can be arranged in memory, which is something that can change the behavior of a program. Capturing all of this non-determinism is important. It's necessary to accurately model LLVM semantics, and it grants additional flexibility for optimizations. So putting this all together, we get an end-to-end specification of an LLVM IR program. This specification is a set which defines all of the allowed behaviors for the program under the semantics. Furthermore, we've also have these verified refinement relations between each layer of interpretation, so between each layer of handling of events. And using these refinements, we can prove behavioral equivalence of programs while leaving certain events abstract, which allows us to ignore things like the particular implementation of memory if it's not relevant. So Vellvm currently supports a large subset of the sequential LLVM IR. If you compile a C program to LLVM IR, there's a very good chance that we support all of the LLVM features that it uses, except for some specific library functions like operating system things. Vellvm has a rich memory model that we published at the previous ICFP that should allow us to verify optimization passes, even in the presence of troublesome low-level memory operations like casts between pointers and integers. And finally, we have a nice interpreter which supports features like printf and command line arguments on LLVM programs, which is useful for debugging. But this also allows Vellvm to be used in testing frameworks like CSmith and YARPGen, as well as our own Gen LLVM, which generate random LLVM IR programs using QuickChick. So Vellvm is a large project. It's under very active development. There's about 50,000 lines of spec and 100,000 lines of proof, according to a WC tool that we found for Rock. A lot of these lines of code are actually in the refinement relations established for the new memory model. And for a sense of the scale and complexity of the proof terms, the VO files total about 500 megabytes, and when gzip, they're about half the size. So throughout this process, one thing that we can't deny is that Rock has been invaluable for understanding the semantics of LLVM at a deep level. Formalization really forces us to address many of the edge cases of the language when we're writing the formal spec. And so this is just a non-exhaustive list of some of the edge cases that have popped up during the development of the semantics. Some of these cases we were able to test for and find miscompilations in Clang, and some issues like address guessing are quite subtle but impact our ability to formally justify optimization passes. At the end of the day, formal specifications demand clarifications to the language specifications, and it keeps us honest. So one example of a small subtlety that came up when we were verifying a compiler for the Helix project, which targeted the Vellvm IR, I guess, so there's two aspects in the informal language reference that lead to a mildly awkward situation. So langref states that we can allocate size 0 objects in memory, but it also states that the pointer that you get back may not be unique. It might be shared amongst other allocations. Langref also states that loading from an uninitialized region of memory should always give undef back. This raises some questions about whether loads of size 0 types always return undef. So in this case, do I always get undef back when loading an uninitialized p pointer here? Or if the p pointer is shared with another allocation, does that, and that allocation was initialized, does that count as initializing this variable and I wouldn't get undef back? It's a little fuzzy. And this case is a bit silly because size 0 values don't store any information, but we had to consider these kind of edge cases when we were verifying the Helix compiler. And ultimately, formalization brings these kinds of subtle issues to light, and similar problems can cause miscompilations. So now we're going to discuss our experience with Rock on such a large project. We don't have much time, but we're hoping to share some points where Rock shines and some struggles that we've had. So Vellvm's a large project, and Rock holds up impressively well. But we've, of course, run into some issues. Some of these are well-known things that sounds like are getting addressed, which is great. The Rock standard library is a little sparse and can be a little light on lemmas. It's also, the standard library also has some performance issues. There's non-tail recursive functions can be pretty common, for instance, which can cause issues with extraction. Compilation time for our project has been an issue. Some of this is certainly my fault, but we've also encountered some bad interactions between Rock features. For instance, using the program fixed point mechanism within a module type ends up generating a bunch of obligations which show up in that module type, which can greatly increase compilation time. Whoops. Rock also has a lot of constraints in order to avoid inconsistencies. And this is a big strength of Rock, of course, but sometimes this leads to tricky situations in longer proofs, which we'll discuss next. So let's just briefly talk about one of the issues that we encountered in the development of Vellvm, where Rock's constraints kind of got in the way a little bit. So the particular details of this example aren't super important, and there's a more complete example at that GitHub repo there if somebody wants to tell me how to do this better. But the gist of it is that the new memory model that we published added a lot of non-determinism to the Vellvm, which added existentials to our refinement relations. And so we ended up with a lot of goals that ended up looking vaguely like this. Ultimately, juggling all of the constraints on co-induction and large elimination of prop and type and so forth proved challenging for the proofs that we wanted to do. We can't use co-induction to invert the relation R because A and B the relation R between A and B because existentials are inductive, and Rock reasonably prevents you from eliminating a co-inductive to construct an inductive type. But even if we just wanted to construct A2 itself, which is an I tree, which is co-inductive, we're not able to do that because we can't extract information from the relation R because R is a prop, and A2 is an I tree, which is in type. And the constraints on large elimination of prop into type disallow this. Maybe this is preventing me from doing something unreasonable, and I don't understand it well enough. But in this particular situation, I think it should be OK, because the type that I'm constructing is just going to be shoved into an existential, which is in prop in the first place. We managed to work around this issue, but the proof ended up being more complex as a result, because we had to reconstruct some of the information that we needed from the equivalent relation in our work. But overall, Rock has enabled the Vellvm project, and we're very impressed with what it can do most of the time. Rock's logic is incredibly rich, and certain aspects of extraction are surprisingly robust in practice, even if it's a little buggy sometimes and we have to patch it up with Perl. Now Gary is going to take over and discuss some of the approaches to testing the Vellvm project.
All right. Hello? Can you? All right. So now that we have a large verified interpreter that is proven to be correct and can evaluate LLVM programs, one key question is how do we ensure that the interpreter adheres to the LLVM IR's informal specifications? For us, testing is the way to go. In Vellvm, we built a large unit test suite that we both develop in-house as well as using the test suites from Alive2. More importantly, we are also using differential testing, test real-world implementations to our implementations to find bugs. Compiler differential testing is not a new topic, and there are some well-known state-of-the-art generation frameworks like CSmith and YARPGen that we are comparing ourselves with. So if we look back to the graphic presentation of Vellum structure, using iTree, we get a verified interpreter for LLVM programs, and we can run programs like this factorial programs through it. We can compare the behaviors of LLVM program run with our interpreter with the behavior under the Klein compiler. If there is any difference in the behavior, that would indicate a bug somewhere. To increase coverage, we will generate many random LLVM IR programs, feeding them into both Vellum interpreter and Klein compiler and see if they differ. Generating LLVM IR program is tricky. Specifically, we need to maintain some property for the programs that we are generating. Most importantly, they should be deterministic so that we can easily compare the output to identify potential discrepancies. We also want our generated programs to be varied and exercise a large subset of the LLVM IR syntax. To this end, we built a tool called GenLLVM for generating random LLVM IR programs on top of the generator monad provided by QuickChick. We also include other features like early terminations and a context-aware metadata system for tracking various properties of the generated variables, such as their types and whether or not they are derived from a pointer for reasons we will soon get into. Due to time constraint, here we briefly show the generation strategy of GenLLVM. This is fairly complicated and involves several mutual recursive functions to ensure expressiveness as well as ensuring well-formedness, for instance, when generating loops. As an example of something that is tricky to generate, consider the example of naively generating into pointer cast from an arbitrary integer. Here we cast an arbitrary integer, in this case 123, into a pointer, which isn't necessarily allocated, so that the program can exhibit undefined behaviors. CSmith and YARPGen both avoid into pointer cast, partly because of this reason. In this case, we need some metadata about how the integer is derived in order to know whether we can cast it into a pointer and read the value pointing to safely and deterministically. There are many state-of-the-art generators, so a natural question is why don't we just use one of them? Well, CSmith and YARPGen actually generate C programs that have to be compiled down to LLVM, and we think that this process can introduce bias in the generated LLVM code, and some instructions may not be well exercised. We've evaluated this hypothesis in GenLLVM as a whole by generating 10,000 programs using each of these generators and comparing the distribution of the LLVM syntax use. We've noticed that we've generated a wider variety of instructions, especially in aggregate data as well as pointer to integer casts. And we've also noticed that our interpreter is fairly efficient. We've also discovered various discrepancies between Klein and Vellum using GenLLVM. Here we are showing an actual bug of Klein that we found using GenLLVM. It's an off by one extract value error. So this code effectively zero initialized a 32-bit pack struct that contains a vector and an integer, and then return the last byte as shown graphically on the right. Because all of the bytes are 0 and we are reading from the last byte, we would expect the return value to be 0. This is the result given by Vellum. However, the executable generated by Klein will output 46 or some random value. When compile this code down to RISC-V, we've discovered that extract value when working with a pack struct with vector can trigger an off by one error. That is, instead of loading a byte from the stack pointer offset by 15 as what is done in the pack struct with array, the generated assembly code is loading a byte from the offset by 16. As you can see graphically, this is incorrect. In contrast, extract value is being compiled correctly when dealing with pack struct with array. So overall, we had a really great experience with Rock Proof Assistant, and that really helps formalizing complex system. Co-induction and interaction trees are helpful in defining semantics, and also Rock's ability to extract executable allows for differential testing, which is essential for debugging and finding bugs in Vellum, Klein, and language reference. These takeaways make Vellum a useful platform for formally understanding LLVM IR semantics. And these are some future works. And if you want to learn more, feel free to visit our GitHub repo or chat with us. Thank you.
Okay, we're running a bit behind, but we have time for a couple questions. So I have one while we move back there. You said it was relatively easy to add new intrinsics. What do you mean by relatively easy?
You basically just like there's a couple of ways that we kind of add new like intrinsics or instructions. You basically just add like a kind of Coq definition for it, and it's relatively easy in the sense that with the new memory model stuff, you have to do one like proof that like this like infinite memory model that we have is refined by a finite memory version of it, and overall it's pretty easy.
Thanks for the talk. I was wondering, you talked a lot about that this is a platform for understanding like the semantics of LLVM. I'm also wondering how much do you like not just think about the semantics, but also about the optimizations and like the things that LLVM is doing. Like, do you have a plan? Like, at some point, you want to have like all the optimizations in LLVM verified in Vellvm, or like, are you working towards that, or in general, what
yeah. So the next steps are kind of like we built all this memory model stuff so that we could verify certain kinds of optimizations, and we're hoping to use that to prove optimizations like mem to reg and stuff. So we currently don't have any verified optimization passes in full, but that's kind of the next step. Yeah.
Time for one more question.
I just have a question, since you seem to use I-trees with non-determinism a lot, and you didn't talk at all about C-trees. Is it something you have looked at? Is there a problem with C-trees that don't make them work for you?
We're definitely considering migrating stuff over to C-trees is the answer. This work was kind of done in parallel with the C-trees work, and we're working on merging stuff.
Just go for it.
And I was wondering about the connection between your work and Alive. Like, is it something you just check whether you say the same thing than Alive at the end, or did you use Alive to design your rock semantic?
So in the Alive project, I think they've generated a lot of like test cases, and some of them are deterministic, and we kind of basically run the deterministic test cases from the Alive.
All right, let's thank the speakers once again.